Okay, we're going to do two more examples that are quick, and then we're going to do a very long example in the next video. So let's look at this polynomial, t cubed plus 12t squared plus 3t plus 6 over q. It's a cubic, so there's one real zero. But all of the coefficients are positive, so there's exactly one real zero. And it's not hard to see also that f is irreducible over q using Eisenstein's criterion with what p is equal to 3. Okay, so the real zero is not rational. What else do we know? We know that there's 3 roots, and we know that if we set G to be the Galois group of the splitting field of F over Q, that we can view this as a subgroup of the symmetric group on 3 letters. And there are 3 such subgroups. They are the trivial group, everything, or the alternating group on 3 letters. So G is one of them. G cannot be trivial because there's at least one zero. So we know G is not trivial. We also know that the size of G is the degree of the extension of the the degree of the splitting field over Q. But there's only one real zero, so the other zeros are complex. So we know already that when we add in our one real zero, the degree is 3, but then we have to add in something new. So this is of course the size of the Galois group, so it has 3 options. It's either 1 if it's a trivial group, it's 3 if it's A3, or it's 6 if it's S3. It cannot be 3 because then that would mean all the zeros are real. So this guy has to be 6. So in particular, G cannot be A3, and so G must be the full symmetric group on 3 letters. So the Galois group we've sort of determined. Up to not writing out what the zeros are, we can reason though with what the Galois group does to the elements of the splitting field. Okay, another quick example. Just to be careful, we saw this already once, but just be careful with making arguments about degree and what subgroup of the symmetric group you get. If you consider the polynomial t to the 5th plus 15t to the 4th plus 85t cubed plus 225t squared plus 274t plus 120 over q, we know that the Galois group of the splitting field, it's called G, the Galois group of the splitting field of F over Q, is a subgroup of S5, right? Because F has 5 roots. But F factors completely. You can probably notice that 120 is 5 factorial. And you'll find F factors as t plus 1, t plus 2, t plus 3, t plus 4 times t plus 5. So all the zeros are rational. There are -1, -2, -3, -4, -5. They're all rational. And the elements of the Galois group have to fix the rationals. So the Galois group is actually the trivial subgroup of S5. When we add in the zeros, the extension is a trivial extension. Okay, so these are 2 other interesting examples. In this first example, we were able to reason what the Galois group was by having knowledge of the subgroup structure of the symmetric group. In this other one, we just are being careful about the degree and making assumptions on what the Galois group must be. In this case, the degree was 5, but the Galois group was trivial.